Hello everyone. So in this lecture, we are going to uh, introduce the continuity and momentum equation in differential form. So previously, we derived these equations in integral form, and in this lecture, what we are going to do, we are going to use divergence or Gauss's theorem, and then convert the integrals to the surface integrals to volume integrals, and then based on that, we will use that to convert the integral forms of the equations into their differential form. Okay, so let's get started. So in order to start that, again, we need this divergence or Gauss's theorem. So for those who might not remember that, I'm going to, from their calculus course, I'm just going to give you a reminder what does that mean and how we are using that. So what this theorem is actually is doing is converting surface integrals to volume integrals. And we would need that when we want to convert the momentum equation, continuity equation in integral form into differential form. Okay. So here, say you have a surface, control volume that looks like this. Okay, and then what this theorem does and what this theorem states, and I'm not going to prove that, I'm just going to use that, is that say you want to evaluate the integral over the surface of this control volume of a vector f, a vector field, say f can be velocity or any vector field, dot the inner product with the normal vector over this control surface. So say you have this, this is the normal vector, so at each point you have this. Okay, and this is your surface. Okay, so this is your surface. And so what you are doing is you are integrating, say this is the so let me modify this a little bit. So say this is n, and then you want, this is ds over the surface. Okay, and then you have another field like f, if f can be velocity or anything that goes through this. So I'm not gonna drive this. So in order to calculate this integral f dot n, so f can be anything, he can have say this could be f. So f dot n over this ds, which is the surface, and this is what you want to calculate the this thing here, and then you are integrating it over the whole surface. So for all these small elements on the surface, so you can convert this actually by using the Gauss's theorem or divergence theorem to an integral over the whole volume of this control volume. So you can take the integral over the volume and calculate the divergence. And this is, we defined this divergence in previous lectures. You can take a look at that. Grad dot f, or divergence of f, in the whole volume of the this control volume. Okay, so this is the volume. So rather than just something on the surface, so if, for example, if you have this something like this in this on the surface, rather than taking just, for example, here on the surfaces, you are getting it over the whole volume of this, the whole volume. Okay, and you need to calculate the divergence of f or grad dot f now in order to calculate that. Okay, so this is the divergence theorem. It's just this equality here, this that you can prove that with and you have and you should have learned it in your calculus 2 especially courses if you have taken a calculus 2 course. But this is what this kind of equality is, and we are going to use it for in our momentum and integral equations in integral form to convert them to differential form. I'm going to show how. Okay, so for example, in the case of say continuity equation, so say we just have the instead of f we just put rho v, the mass flux. Okay, so this we had it in the continuity equation, and that rho v dA over the surface, which using this Gauss's theorem we can write this as the integral over the volume of divergence of or grad dot rho v over dV. Okay, so this is how divergence theorem is going to help us to convert these terms over the surface into the terms over the volume. So similarly, you can show these equalities that I'm going to use. So these are just some mathematical equalities that we are going to use here. I'm not going to prove them here. So NPdA, this is the other thing we had in momentum equation, which was over the surface. So you can write it over the volume as this grad P dV. And you can write the integral of n, the curl of n with v, or n cross v dA. This equals to curl of n cross v equals to curl of v dV. This we call it curl. Okay. So this is how you actually are converting surface integrals, which are on the left of all of these equalities, into volume integrals. Okay, so this is what this is an equality and a theorem we want to use in order to convert the integral equations into differential form. Okay. So having these equalities and this theorem in mind, we can start with the first task we have, which is continuity equation. In differential form. So what was the integral form? So first I want to start with the integral form of continuity. I can go and find it. Here, this is the integral form of continuity equation. Okay, so I will start with that. And then I am going to use Divergence Theorem. So for this term, I'm just going to write, we had it here, so I'm just going to write this one. So instead of this, I'm going to write this term for the second term. And then for the first term, I'm just going to write it down. So the partial t integral of rho dv plus this equals to 0. Okay, so since dv is fixed, the only thing in this equation that varies is rho. So I can just write this as this one. I can write it as the integral of rho. I can take the partial over partial t inside the integral and just write it as this. Rho v dv equals to 0. Okay. So again, the reason is the only variable part, since dv is fixed. Okay. And now I can just combine these two because they are over the control volume. So these integrals are over control volume, right? So let me start from the beginning. This was over the control volume, this was over the control surface, and then this is over control volume, and this one was over the control volume. But using divergence theorem, we changed the surface integral into the volume integral. And so I can just combine them together and write the integral over the control volume of partial over partial t of rho plus the divergence of rho v dv equals to 0. Okay. This is an interesting equation now. And now, so since this has to be 0 for any arbitrary dv, so for any dv you choose, this equality has to hold, right? So the only way this can be true is that the integrand must be 0 too. Because this is true for any arbitrary dv you take, for any arbitrary cv you take. So it's the only way this can be true is that the integrand itself, which is this one, must be 0. So this means that partial over partial t of rho plus divergence of rho v equals to 0. And what it is? This is a very important equation. This is actually continuity equation in differential form. This is what we were seeking, okay? So if you want to write the continuity in differential form, this is the form of that. And then we can write it in other forms as well. So say v, the velocity vector, is a 3D velocity vector, right? So we can write it its component as UVW. So if you have, this is X, Y, Z. So if you have a velocity vector, so you can write it in this way. So this is, let me extend this a little bit. So this is gonna be U in the X. In the Y, this is gonna be V. And in the Z direction, which is the vertical direction, this is gonna be W, okay? So this is our velocity vector. So it has three components, U, V, W, as you can see it here, okay? So I can now write this partial over partial T of rho plus divergence of rho V. This equals to partial rho partial T plus, so divergence of rho V. So rho V is UVW, and then the grad dot is just a dot product between the grad operator and this velocity vector. So it's gonna be partial over partial rho U. This is the first component. Or partial X plus partial rho V over partial Y plus partial rho W over partial Z. Okay? And so now I can use the differentiation rule to write this as sum of two terms. So first one is going to be rho partial T plus the first part is going to be U partial rho partial X, and then the second one is going to be rho partial U over partial X, which I'm going to write later. So let me just first write this, V partial rho partial Y plus W partial rho partial Z. And then the second part is going to be this rho, because this is the derivative of two terms. So the second part is going to be rho partial U over partial X plus rho partial V over partial Y plus rho partial W over partial Z. Okay? And what is this? What is this? And what is this? We know this from before. One is total derivative. Let me bring this. Yeah, this one, you see it, right? This is dv over dt. Okay, so instead of v, the velocity vector here, just put rho, and you are gonna get the same thing as we got before. So d rho dt is gonna be exactly like this. And what is the second term? So the second term is, if you remember, let me see if I have it. If I've defined, yeah, divergence, I have it here, right? This is the divergence. Divergence of V is gonna be grad dot that vector. So it's gonna be exactly, just let me show it to you. They are actually similar, right? This is just divergence of velocity vector, okay? So I can write this as rho divergence of V. And for this is just d rho over dt. So this equals to d rho over dt, total derivative or material derivative, plus rho divergence of velocity vector equals to 0. So this gives me another form of the continuity equation, and that is as follows. So 1 over rho d rho over dt, the total derivative of rho, equals to minus divergence of velocity vector. So this is alternate form of the continuity equation. Just look at it. So this was the first form, and this is the alternate form of that. Okay. So now we want to define, based on these equations, incompressible flows. What do incompressibility mean? So incompressible flows. Remember, I'm talking about flows, incompressible flows. So let's see what do they mean and how we define them. So incompressible flows, for example, like air and water, these are incompressible flows, are defined as this. We define them as, we call a flow incompressible if the divergence of the velocity vector of that is equals to 0. Okay, so this means that the total derivative or material derivative of density with respect to time should be 0. This means that if you follow a particle, fluid particle, its density has to be constant. But rho or density may change spatially, but the flow is incompressible. What does this mean? This means that based on this equation that you have here, okay, so you might have a flow where this is not 0, d rho, for example, or let's say partial rho over partial x is not 0, okay, but your flow is somehow incompressible because the other terms, these terms, make the whole d rho over dt 0. Okay, so this is what we actually care about incompressibility, not the spatial variation in one direction. So it's the whole thing in the flow that we consider, in the density that we consider. So this is the incompressibility. So rho may change spatially, but the flow is incompressible. So it's more than just something you may have thought that rho equals to zero, rho equals to constant. If your rho is constant in the whole flow, that's definitely incompressible, okay? But this is just a spatial case. This is just a special case. This is just a special case of incompressible flow. So that's definitely incompressible, but incompressible flows are more than just rho is constant in time and space. So rho may change spatially, like here as I showed, but in total, the total derivative or the material derivative of rho with respect to time should be zero, okay? Also, there is another way to show this divergence. So we can show it using the Einstein's index. So we can show it as partial uk over partial xk equals to 0. This is an alternate form of showing incompressible flows. And this is actually with what we call Einstein's index notation. It's just a simplification of this type of approach where we have these grads. We can just write them using Einstein's index notation, which I think is easier to understand, because here you can just show it with an index like k, and this index just shows a sum. So this actually means it's partial u1 over, so k goes from, say, 1 to 3, 1, 2, 3. So this means this is rho u1 over rho x1 plus partial u2 over partial x2 plus partial u3 over partial x3 equals to 0. And these are the velocity components of the total velocity vector, or we can write it as we had it before. It's partial u, partial x. The second component is v, partial v over partial y. And then the third component of velocity vector is w, so it's going to be partial w, partial z equals to 0. So just remember, your velocity vector is this, it has three components, u1, u2, u3, which we wrote it as u, v, w. Okay. So this is actually another notation for divergence of v equals to 0. I think it's a simpler notation, but it's up to you which one you want to use. And this is, again, an alternate form of continuity equation, incompressible flow condition. Okay, so here up so far we showed the differential form of continuity equation in two forms. The first one is this, and second form is this here. And now in the next session I'm going to derive the differential form of the momentum equation. Especially when we don't have viscosity, we are going to derive the Euler equation.